Hello, my name is Amy Tabb, and I'm presenting joint work with Henry Medeiros. So I'm from a U.S. Department of Agriculture lab, and Henry is from Marquette University, and I'm going to tell you about a method we developed for curve skeletonization. So just a brief introduction about curve skeletonization. So in curve skeletons are generally locally one-dimensional representations of three-dimensional objects, and skeletons of three-dimensional objects can be locally planar. And so there's a long and rich history of work on curve skeletons. They can be for different representations of three-dimensional objects, either mesh, point clouds, or voxel-based representations. There's not an agreement about what a curved skeleton is, so within the literature there's various different goals for computing curved skeletons. And there's also, there's different communities in terms of curved skeleton work, computer graphics, computer vision, and also computational geometry. And within those communities, there's usually an assumption of noiseless surfaces and long or unreported computational times. So in our work, we have goals of using the curved skeleton as part of an agricultural automation problem, and so we have particular assumptions that we want to operate on voxels and that our surfaces have noise. And we also want a fast method that can handle loops. So the existing work didn't have any of these requirements, so we worked on a method. And our method is a path-based algorithm, and I'll show you a video in a second. And it's quite robust to noise. It only has one parameter, it's sort of a coarse parameter that represents the degree of noise that's on the surface. And it can handle loops and doesn't have an additional pruning step. So I'll show you a video now. So this is about a 10 times slowdown of how the algorithm, how fast the algorithm is. So for this particular object, it only takes to about 2 seconds to run. So it adds the longest paths first, and then over time adds the shorter paths. And so this is the result for a tree. So this is part of a bigger project for computing measurements of tree structures which have noise, because we're acquiring them outdoors. So we did extensive comparisons to the state of the art, and here's a graph that represents the runtime of our method compared to our other methods. So our method is shown in green, and you can see that it compares very favorably to other methods. And so the full paper and our very, very long supplemental material, that's 37 pages or so, is available on arXiv if you're interested. And the code is online, so you're welcome to use it if it's useful in your work, and come by and see us at the poster, and want to acknowledge the funding source of an NSF grant. Thank you.